Welcome to lecture 18. In this lecture, I will start the derivation of the Einstein Field Equations. Recall that we found that the energy momentum tensor on a curved manifold is covariantly conserved. So the covariant derivative acting on the energy momentum tensor is equal to 0. We also found that there is a second conservation law where, or rather a statement where the covariant derivative acting on the metric tensor is equal to 0. This is not strictly speaking a conservation law, but if we take one of these indices alpha to be equal to mu, we can write it in the form that appears similar to a conservation law. So since we have these two quantities that vanish on the action of the covariant derivative, this begs the question whether there are any other rank 2 tensors that vanish under the action of this covariant derivative. The answer to this question is yes, but it turns out that it is quite a bit of hard work to find the explicit form of this rank 2 tensor that also vanishes under the action of the covariant derivative. Nevertheless, I think it is instructive to be able to follow the derivation of this because we will need this as a main building block of the Einstein Field Equations, so we will perform this hard task in the present lecture. To get started, let me introduce the concept of a commutator, where the commutator of two quantities, nabla mu, nabla nu in this case, is defined as the action of the two operators nabla mu, nabla nu, minus the one where the order of the operators is exchanged. So we have nabla nu, nabla mu with the other index order in this case. Next, note that we can write commutators strung together. So here we have the commutator of a commutator acting on some vector v. And we can take different combinations of these commutators. So in this particular case, the index order here was mu, nu, lambda. Next one is nu, lambda, mu. So basically I have just shifted all the indices to the left and sort of put the index that is to the very left all the way to the right. I can do this once more. So then I have lambda, mu, nu acting on the vector. And the claim is the sum of these three terms will turn out to be equal to 0. We can show that this is a true statement in the following form. I will introduce some more compact notation for this. The notation I'll choose is that instead of writing all the symbols for the covariant derivatives here, I will just write down the indices that these covariant derivatives carry in order to write down this more compactly. So in particular, for a piece of this first commutator here, I will have mu, nu, lambda, mu, nu, lambda. And then because this commutator also includes a term that's minus d lambda d nu, I have minus mu lambda nu for expanding out this first commutator here. This will give me two terms. I can do this for all the terms here. So in particular here, I have a second term where I have the commutator acting on nabla mu on the right-hand side. This will give these two terms. And then I have many more terms from expanding out the other two structures that I have in here. Doing so, you can now look at these ordering of the symbols and see whether there is any cancellations occurring. In particular, look at this term here, which I note structure number 1. And then you look at all of the terms if there's a similar structure here. Indeed, we find one there. Here also we have mu, nu, lambda, and it comes in with a minus sign, whereas this one comes in as a plus sign. So that means that these two terms just cancel each other explicitly. Next, look at this term here, which is mu, lambda, nu. And indeed, there is a term mu, lambda, nu, which has the opposite sign. So these two terms cancel. Next, lambda, nu, lambda, mu, which cancels against this term here, and so on and so forth. You can verify that indeed all these combinations just cancel each other and you get 0, proving the statement that these combination of structures just vanishes. This equation 18.4 has a name. It is known as a Bianchi identity, and it will be our central building blocks for the following math. The next thing we want to do is we want to look at one of these commutator structures, and we want to expand this in terms of the Christoffel symbols. So in particular here, from the commutator, we have mu nu minus mu acting on sigma. When we expand these covariant derivative, we get ordinary derivative, and we get Christoffel symbols, both for this first one here and the second one over there. Now we still have more covariant derivatives left, so we also want to expand those. So in particular here we get a term that's partial mu, partial nu acting on v rho, and so on and so forth. Many terms. However, many of these terms in this expansion actually again cancel. One of them you can see as follows. There's this term with two derivatives, mu nu acting on the vector v rho from this term. And here we have a term with two derivatives, nu mu acting on v rho, but the partial derivatives themselves are commuting with respect to each other. So that means that this two derivative term from this combination cancels against the two derivative term from this combination. And there are more of these cancellations occurring, so that at the end of the day, we find that this combination here just has four non-vanishing structures that are left after everything that cancels is taken out. These are two derivatives of the Christoffel symbols and two terms where we have Christoffel symbols squared. Since I don't want to write down this lengthy combination here, I'll give this combination a name. I'll call it R, rho, sigma, mu, nu, for the indices rho, sigma, mu, nu appearing in the expression in these parentheses. And this is the shorthand notation that I'll be using in the rest of the lecture. So now that we have the shorthand notation, we can write down the Bianchi identity as a sum of three such terms, where we have replaced one of these commutator terms in terms of this tensor R, and then here that is the remaining part of those commutators, and we have three copies of this for the cyclically shifted indices. Now let's look at these other parts in here. Here we have this commutator of covariant derivatives acting on a derivative of a vector, not on the vector itself. If this was a vector, we could just use the same R tensor as we have before, but now we have two vectors. So we have one where we can sort of replace this as a tensor R, where we have acted on the V rho here. So rho is the index that appeared in here, and I must have done something wrong here. So clearly the rho must be at a different position than appearing in this expression. But the second term is presumably the right one, where this acts on the covariant derivative with a mu downstairs. So that gives us, instead of a rho here, the mu is downstairs. So the second expression is correct here. We can use the properties of this R tensor to show that the R is antisymmetric in the first two and last two indices. So in particular, R mu downstairs, rho upstairs is minus R rho upstairs, mu downstairs, which we have used in the second equation here. Also, we can look at one of these structures here, for instance, this one, and use the chain rule so that the covariant derivative is first acting on the R tensor, that's this term here, and then a second term where the covariant derivative is acting on the vector. And the point I want you to take away is that this structure here is basically very similar to that structure there if you ignore the typo in these indices. So that's important because it turns out that this structure is the same as that one over here, regard the minus sign, whereas that one is the same as that over there. So if these two terms are equal to each other and there's a minus sign here, it means that this term will exactly cancel against that term. And what we have left, if we look at this first combination, is the sum of these two terms. So we replace this by a term that is the derivative of the R tensor and a term that is R times the derivative of the vector. And we have 3 copies of these with different index locations, so that if we sum all of these up, our Bianchi identity becomes the following equation. It is one where we have the vector and 3 derivatives of the R tensor, plus 3 versions of the R tensor acting on the derivative of the vector itself. Next, it is possible to again use the explicit form of the R tensor to show that if we have R with cyclic indices appearing in this particular fashion, the combination that involves only pluses is just identically vanishing. So if we use this, then it means that that second piece of the Bianchi identity is just 0, and our Bianchi identity becomes just a statement on the derivative of this R tensor, because this vector in front here is arbitrary, and if the vector times this combination of derivatives is vanishing, then since the vector is arbitrary, the combination of these derivatives themselves must be vanishing. So now we have this combination of derivatives from our Bianchi identity. We now contract this with a metric tensor, and we want to pull it through the covariant derivatives using the fact that the covariant derivative on the vector itself is vanishing. So if we do this, if you pull in this first metric in here, the first tensor, means we replace the sigma downstairs by a new upstairs. So this is what's happening from here to there. Then from the second term, we replace the nabla new downstairs by nabla sigma upstairs. And for the third term, we use it to again replace the sigma downstairs by new upstairs. So that's these 3 terms here. Next, again, we contract with another metric tensor, and we again use the property that the R tensor is antisymmetric in the indices, the first 2 indices and the last 2 indices. So we do this. If we contract the first term up here with G mu rho, we replace the rho by mu, and we replace the order nu and mu, picking up a minus sign, so we get this first term here. For the second term, we replace the rho by mu, so we get a mu, and we replace the order mu and lambda, so we get mu and we get so we have mu here. Okay, so something must be wrong with that term, but if we look at this third term here, we have G mu rho acting on this last term here, and we can replace rho by mu, and we have the mu nu over there, so as before. Yes, I think this must be a mu. Okay, so if we then define a particular contraction of these R's as appearing in this equation by introducing some more shorthand notations, we find the following results. So in particular, we find that if we define the contraction of the first and third index to be R mu nu, and if we define the complete contraction of this as R, we can recognize this thing to be R, and these just be cases of R mu nu. So in particular, we find here that we have this first term being R mu lambda for this first term here. And here, if we disregard the fact that this should be a mu, we have R sigma lambda from the second term. And here we could just nabla lambda on R. Since sigma and mu are completely contracted in these first 2 cases here, we can change the upstairs downstairs orders because they don't matter, and we can change the label. So for instance, we can replace sigma by the label mu, so then these 2 terms are twice the same term, and we get minus nabla mu twice R mu lambda, and we write this term in the same form, so we have to introduce a new metric tensor to change the index mu to lambda for that. Okay, so after the dust settles, what we find is that we have a covariant derivative acting on this following combination here is just 0. So that is the sought after third identity that was promised in the first slide of the present lecture. And we will use this difficult to extract result in the next lecture to build the Einstein field equations. And that concludes the present lecture.